Dr. Anthony Raj. He has pursued his bachelor's, master's and MPhil in physics. He then went on to pursue his PhD in physics at the University of Madras as well. He then went on to work as a lecturer at Thiruvalluvar Arts and Science College and Idya Engineering College for Women. Since the year 2006, he works as the lecturer and assistant professor at Loyola College, Chennai. With regard to research, he has published several papers in international journals, namely Radio Wave Propagation over Salem, Linear and Non-Linear Optical Properties of Pure and Doped Selenium Malate Single Crystals, and many more. He has also attended several conferences and seminars, namely International Conference on Materials Science and Technology, National Conference on Higher Education at Crossroads held at Loyola College, National Seminar on Crystal Growth 12 held at VIT University, and many more.
Welcome to UGC lecture series BSc Physics Honours Mathematical Physics 2 Semester 2 Lecture 13. In this lecture we are going to see concepts of Lagrangian. In that concepts of Lagrangian, introduction about Lagrangian concepts, equation of motion of a system of particles, then constraints of motion, degrees of freedom and generalized to coordinates, then summary. These are all the topics we are going to discuss in this lecture. Concepts of Lagrangian. We know mechanics is a branch of applied mathematics, deals with the motion of a particle or a system of particle with the forces. To discuss the motion of a bullet, a physicist is in need of many experiments. To know the velocity of the bullet, he need to find the distance travelled by the bullet and time taken by the bullet. Then he need to find the time of flight of the bullet. Like that, many experimental procedures a physicist has to adapt to understand or to analyze the motion of a bullet. But for a mathematician or mathematical physicist, just any point on the path of the bullet is enough to explain all the parameters of the bullet. So here let P of x comma y be any point on the path of the bullet. The only force acting on the bullet is the gravitational force. If the bullet is stationary, gravitational force is the only force acting on the bullet. Suppose the bullet is moving horizontally, fired by the gun, force given by the gun and the gravitational force. These are the two forces acting on the bullet. So let us take a bullet on which only gravitational force acts, then the direction of the gravitational force will be in downward direction. Then the gravitational force can be resolved into components. We know in physics any vector quantity is inclined with some angle can be resolved into components. Like that, here the gravitational force of the bullet is resolved into components. Resolving this force horizontally and vertically, we write from Newton's second law of motion the equations of the motion. We know the Newton's second law of motion. Newton's second law of motion says that rate of change of momentum of a body is equal to force applied on the body. This is Newton's second law of motion. According to Newton's second law of motion, the equation of motion of the bullet is written like this, that is d square x by dt square is equal to 0 and d square y by dt square is equal to minus g. These two equations of motion says that the rate of variation of distance horizontally, that is horizontal distance variation with respect to time is 0 for the bullet, then vertical distance variation is equal to negative of the acceleration due to gravity. This is the concept explained by these two equations. These two equations are obtained from Newton's second law of motion. Integrating these two equations and using the initial conditions, we readily obtain the dx by dt, where dx by dt says the rate of change of horizontal displacement with respect to time. Dx by dt is equal to u cos alpha, then dy by dt is equal to u sin alpha minus gt. These are the equations we obtain after integrating these two equations and substituting the initial conditions, where u is the initial velocity in this equation when time t is equal to 0. Integrating equation 2 once again and using the initial conditions, we obtain x is equal to u cos x alpha t, y is equal to u sin alpha t minus half gt square. These two are the equations we obtain after integrating the two equations. These two equations says that the horizontal displacement and vertical displacement. Here horizontal displacement is a function of the initial velocity u and the angle subtended by the bullet with the horizontal axis. Alpha is the angle subtended by the bullet with the horizontal axis. So, x is equal to u cos x alpha t, y is equal to u sin alpha t minus half gt square. This y is equal to u sin alpha t minus half gt square is similar to the fundamental equations of motion y is equal to ut plus half gt square, where here instead of that u sin alpha is given, then t comes as it is, then minus sign comes because the bullet moves against the acceleration due to gravity. These two are the equations we obtain after integrating equations 2. The equation 2s are dx by dt is equal to u cos alpha, dy by dt is equal to u sin alpha minus gt. These two equations are obtained after integrating these two Newton's second law of motion and substituting the initial condition in that equation. The equations 2 determine the velocity of the bullet at any time t, while equations 3 and 4 determine the position of the bullet at that time. Further, eliminating the t from these two equations 3 and 4, we get y is equal to x tan alpha minus half gx square by u square cos square alpha. This equation gives the trajectory of the bullet, the trajectory traced out by the bullet. This equation is similar to the equation of a parabola. So, this equation gives the path of the bullet and the path is a parabola. We know the parametric equation of parabola is y square is equal to 4ax, x square is equal to 4ay, like that. Different parametric equations are there for parabola. This equation is analogous to the parametric equation of the parabola. Hence, we can conclude that the path traced out by the bullet is similar to parabola or equal to parabola. So, from these analyses, we learned that by assuming a coordinate, we can obtain the position of the bullet, velocity of the bullet, acceleration of the bullet, displacement of the bullet, the path traced out by the bullet, like that. Many parameters can be mathematically calculated by just knowing only one positional coordinate of the bullet. That is the beauty of mathematical physics than experimental physics. Experimental physics is in need of many instruments to analyze the various parameters of the bullet here, but in general various parameters of a moving body. But in mathematics, by using simple mathematical calculations, we can bring equations to explain the various parameters like position, velocity, acceleration, all these things. This is what this mechanics deals. So, mechanics is a branch of mathematical physics which deals with the motion of a particle. This is how various components of motion is obtained from the mathematical treatment of a bullet. Now, equation of motion of a system of particles. In the previous topic, we just learned what is mechanics, how mechanics can be easily performed. Now, we will get into the basic part of mechanics, that is equation of motion of a system of particles. Consider a system of n particles of masses m1, m2, etc., mn having position vectors Ri, where I is equal to 1, 2, 3, etc. n relates to an arbitrary fixed origin. Here in this equation of motion of a system of particles, we can imagine a bullet. There bullet is assumed as a single entity, but here we are going to assume the same bullet made up of many particles, innumerable particles. So analysis of that innumerable particle gives the equation of motion of a system of particles. For that, in general, we are considering a system which has n particles. Masses of those n particles are m1, m2, etc., mn. Then position vectors are r1, r2, r3, etc., rn. This position vector relates the system of particles to an arbitrary fixed origin. In that system of particle, any particle will experience two types of forces. The first force is external force on the system. That external force on the system is denoted by F suffix I, E. This is the denotion of external force, where I can be 1, 2, 3, etc., n. So if you substitute that I here, we can get F1E, F2E, F3E, where F1E says the external force acting on the particle 1, F2E says external force acting on the particle 2, like that F1E says external force acting on the particle n. So this is the first type of force acting on a system of particles. The second type of force is internal forces. Here internal forces means in the system we assumed we have n number of particles. Out of that n number of particles, just imagine only one particle. On that particle, remaining n minus 1 particles will exert a force. Such forces are called as internal forces. So this is another kind of force that acts on this system of force. So in these internal forces are represented by F suffix I comma j. Thus, the total force acting on the ith particle due to the interaction of all other n minus 1 particles of the system is called the internal forces. These are the two types of forces acting on a system of particles. Here we are going to derive the equation of motion of a system of particle. For that, first we assumed n number of particles, masses of those particles, position vector of those particles, and the forces acting on the system of particles, and we found that two types of forces are acting. One is external force, another one is internal force. Thus, the equation of motion of the ith particle is given by summation of the external force and internal force is equal to rate of change of momentum. This gives the Newton's second law of motion for a system of particles. So Fie is the external force acting on the ith particle plus summation of j, Fij internal is equal to dpi by dt. This is the equation of motion of the ith particle. The equation of motion of the whole system is obtained by summing over I the equation 1. We get summation of I Fie plus summation over I summation over j Fij internal is equal to summation over I dpi by dt. This is the equation of motion for the whole system of particles. This equation of motion is for the ith particle. Here we summed up the equation of motion to the whole particle. Just put if the system contains only one particle, then you can substitute F1e plus say summation over 1 summation, then F1 internal is equal to summation dpi. If the system consists of two particles, we need to add the force on the first particle and second particle. Like that we need to do mathematics to get the equation of motion of the whole system. We write this equation as summation over I Fie plus summation over ij, where I must not be equal to j. Fij internal is equal to summation over I dpi by dt. This is how the equation of motion for the whole system of particles will turn up. Here you can see that I is not equal to j. Here this I is not equal to j says that particle itself will not exert any force on itself. That is the meaning of this I is not equal to j. Only the next particle can exert force on one particle. That particle itself will not exert force on itself. That is the meaning of this. So that equation will change to this form. So the term summation ij, I not equal to j, Fij represents the vector sum of all the interaction forces due to the presence of remaining n minus 1 number of particles. If a system consists of n number of particles, assume one particle in that system, remaining n minus 1 number of particles will exert force on that. So also the internal forces obey the Newton's third law of motion, which says that every action has an equal and opposite reaction. Thus the action of one particle on the other is equal but opposite to the action of second on the first. So this is how Newton's third law of motion is obeyed by the internal forces. This implies that the mutual interaction between the ith and jth particles are equal and opposite. That is Fji internal is equal to minus Fij internal. If you take this as the force exerted on ith particle by jth particle, then that will be equal to negative of the force exerted on jth particle by the ith particle. This is what Newton's third law of motion says. This third law of motion is obeyed by the internal forces. So we got this equation. This gives summation over I comma j, I is not equal to j, Fij internal is equal to 0. Thus equation of motion of the system of particles becomes summation over I Fie, that is sum of the external force on the ith particle is equal to sum of the rate of change of momentum on the ith particle. So the equation of motion of the system of particles becomes Fe is equal to dpi by dt, where p is the total momentum of the system and Fe is equal to dpi by dt is the total external force acting on the system. This is how we can get the equation of motion for a system of particle. So from these two topics we just learned what is mechanics and how to obtain the equation of motion for a system of particle. The next important concept in Lagrange's formalism is constrained motion. Sometimes the motion of a particle of some system of particles is not free, but it is limited by putting some restrictions on the position coordinates of the particle or system of particle. That is, every motion is not a free motion. Few motions are disturbed by some parameter of the system. That is what this constrained motion says. So the motion under such restriction is called constrained motion. So the constrained motion is defined as the motion of a particle of a system of particles is not free sometime, but it is limited by putting some restriction on the position coordinates of the particle or system of particle. The motion under such restriction is called constrained motion. There is a mathematical relation to explain this constrained motion. In the previous topic, we learned a mathematical relation for the motion of the particle. Like that, constraints can also be included in the equations of motion. So, the mathematical relations for this constraint is the mathematical relations establishing the limitation on the position coordinates are called as the equations of constraints. Relations establishing the limitations on the position coordinates are called as the equations of constraints. So, mathematically, the constraints are the relation between the coordinates and the time t. Consequently, all the coordinates are not linearly independent. Constraint relation relates some of them. Thus, in general, the constraints on the motion of a particle or system of particles are always possible to express in the form f suffix I is equal to xi, yi, zi, t will be less than or equal to 0 or greater than or equal to 0 or equal to 0. In any of these three forms, the constraints of the motion can be equationally represented, where t is equal to 1, 2, 3, k, etc. k gives the number of constraints, and xi, yi, zi are the position coordinates of the ith particle of the system, where I can be 1, 2, 3, etc. n. So, this is the mathematical relation expressing the constraints of a motion. Examples of motion under constraints. The motion of a rigid body. For the motion of a rigid body, frictional force between the body and the surface of motion will be a constraint. Then the motion of a simple pendulum, air resistance will be the constraints for the motion of the simple pendulum. If there is no air resistance, then the simple pendulum will move freely. So, in that case we can say the simple pendulum has a constrained free motion, but in practical the motion of a simple pendulum is a constrained motion. Then the motion of a particle along the parabola, x square is equal to 4ay. We know that the parabola has a cave-like structure. So, when a body comes to that cave part, it need to overcome the constraint given by the cave part to raise to the upper part from. So, it need to descend one part and ascend one part. In between the descending and ascending, there is a cave-like structure. To ascend, it needs some extra force. That need of extra force is a constraint in that motion of a particle along the parabola. Then motion of a particle on the surface of a sphere. This is also an example for motion under constraints. So, these are all the examples of motion under constraint. Then classification of constraints. In general, the constraints can be classified as holonomic and non-holonomic constraints. These are all parts of Lagrangian formalism, which is that Lagrangian formalism is an important concept in variational calculus. So, constraints can be classified as holonomic and non-holonomic constraints. Holonomic constraints. If the constraint on a system of particles or on a particle are expressible as an equation in this form, then that constraint is called as holonomic constraint. Fi is equal to xi, yi, zi, t is equal to 0 is the equation used to express the holonomic constraints. That is, if a constraint is expressible as this equation, then that constraint is called as holonomic constraints. Otherwise, those constraints are called as non-holonomic constraints. This is how the constraints can be equationally represented in variational calculus. Degrees of freedom and generalized coordinates. These two are other important concepts in variational calculus, especially in Lagrangian formalism. Degrees of freedom. the least possible number of independent coordinates required to specify the motion of a system completely by taking into account the constraints is called degrees of freedom. This is the definition of degrees of freedom. So, number of independent coordinates required to specify the motion of the system by taking into account the constraints is called the degrees of freedoms. Example for this degrees of freedom: for a system of n particles free from constraints moving independent of each other has 3n degrees of constraint. If you take a three-dimensional space, in that three-dimensional space a particle is moving, so that particle position is represented by 3 coordinates. So, the number of degrees of freedoms for that particle is 3 into 3 degrees of freedom, which is equal to 9 degrees of freedom. So, the number of possible independent coordinates required to specify the position of the system completely by taking into account the consideration is called degrees of freedom. Next, generalized coordinates. We know in general there are parameters or coordinates used to represent the position or the movement of a particle in space. In generalized coordinates, apart from the coordinates, other parameters can also be used as coordinates. That is what this generalized coordinate says. So, consider a system of particles, n number of particles are there, those n number of particles are free from constraints. So, number of degrees of freedom for that n number of particles are 3n degrees of freedom. If there exist k holonomic constraints expressed in k equations, that is Fi of R1, R2, etc. Rn t is equal to 0, where I is equal to 1, 2, etc. k, keep this as equation 1, then the 3n coordinates are not all independent, but related by k equations given in this equation 1. This is the general form of the k equations. If you substitute I is equal to 1, you will get one equation. Then I is equal to 2, second equation. I is equal to 3, third equation. Like that, if you keep on substitute the value of I till k, you will find k equations. These k equations used to represent the coordinates, 3n coordinates independent. So, these k equations can be used to eliminate k of this 3n minus k is equal to n independent coordinates. So, these are generally denoted by qi is equal to q1, q2, q3 like that. This is how the generalized coordinates can be represented. Thus, the generalized coordinates can be defined as generalized coordinates as the 3n minus k independent coordinates q1, q2, etc. qn sufficient to specify completely the configuration of a dynamical system. This is how the generalized coordinates can be defined. This is another important parameter in Lagrangian formalism. Summary. In this lecture, we learnt the Lagrangian formalism. That Lagrangian formalism involves scalar rather than vectors. In Newtonian mechanics, vectors are used. In Lagrangian formalism, scalars are used. So that Lagrangian formalism, Lagrangian mechanism is easy to work out, easy to calculate. Then we learnt about constraints. Those constraints are parameters which restricts the motion of a body. There are two types of constraints: holonomic constraints and non-holonomic constraints. Generalized coordinates. This is the next concept we learnt in this lecture. Generalized coordinates are used to specify the dynamics of a body. Those generalized coordinates are coordinates used to specify the dynamics of a body. Other parameters can also be used as generalized coordinates. These are all the concepts we learnt in this lecture. So, after listening to this lecture, we can answer the following questions: what is known as constraints? Define generalized coordinates. Give Lagrange's equation of motion. Thank you.